Take a look at the man you see on your screen. Who is he? Here's a hint, he's dead. Here's another hint. If it weren't for him, you wouldn't be watching this video. Give up? He was a French scientist and philosopher named Blaise Pascal, who died in 1662. Among his many accomplishments was the discovery of the fundamental principle governing the two works of art you see here. We'll tell you more in a moment. This video is designed to provide a basic understanding of hydraulics for operators of radial boom derricks, otherwise known as digger derricks, or RBDs, and users of insulated aerial devices, commonly called bucket trucks. While it can be used for self-study, its main purpose is to augment in-class and hands-on sessions. Here are some topics we will cover. Fundamental hydraulic principles, basic hydraulic systems, inspecting hydraulic systems, holding valve checks, operating tips. Let's start with the key principle underlying all hydraulic equipment. Known as Pascal's principle, it states that pressure applied to an enclosed fluid is transmitted undiminished throughout the fluid and to the walls of its container. While this may sound like a mouthful, the idea is really very straightforward. For example, in the setup you see here, if a weight is added to the piston, the pressure increase is the same everywhere in the cylinder. The practical importance of this statement becomes more apparent when two pistons are connected. If you put a light weight on the small piston, you can lift a much heavier weight on the large piston. How can this be? The reason is that the increased pressure exerted on the fluid by the small piston is equal to the force on the piston divided by its face area. Say, for example, in our test setup, the weight on the small piston is 10 pounds. Its face area is 1 square inch, and the face area of the large piston is 5 square inches. The increased pressure exerted by the small piston is 10 psi. This pressure is transmitted undiminished to the large piston. The increased force on the large piston is equal to its face area times the increased fluid pressure. As you can see, this works out to 50 pounds. The transmitted force is magnified 5 times. Because of this ability to magnify force, hydraulic power transmission is used in many different kinds of machinery. But from a utilities standpoint, hydraulic systems have two special advantages: mobility and dielectric strength. Going back to the two-piston setup, keep in mind that the connection between the pistons does not have to be rigid. In utility work, for instance, most hydraulic hoses are made of neoprene. What this means is that a relatively small stationary power supply can deliver large amounts of power to moving components. And there is one other advantage of hydraulic power transmission that makes it especially attractive from a utility standpoint. If the materials used meet the appropriate standards, the hoses and hydraulic fluid are non-conductive. That's as much as we're going to say about hydraulic theory. When we come back, we'll look at a basic hydraulic system. In the previous section, we used this simple setup to demonstrate basic hydraulic principles. In the real world, of course, hydraulic systems are much more complex. In this section and the next one, we will focus on the main system components and protective devices. This diagram shows the four main components of a typical hydraulic system: the pump, the cylinder, the control valve, and the reservoir. Let's go through them step by step, starting with the pump. A typical hydraulic pump uses a system of gears, vanes, or pistons to move the hydraulic fluid from the pump inlet to the outlet. The pump shown here is known as a positive displacement gear pump. Positive displacement means the pump delivers a constant volume of fluid with each revolution, regardless of the downstream resistance. You will find out why this characteristic is important when we talk about relief valves later on. The cylinder converts fluid pressure into linear motion. By diverting hydraulic fluid into the upper and lower chambers of the cylinder, the operator can move the piston and the attached piston rod up and down. The component used to direct the fluid is the control valve. The valve shown in this simplified graphic is an open center valve. It has 3 operating positions. When the valve is in the neutral position, fluid flows around the valve spool and back to the reservoir. Now watch the direction of flow change as the control valve is moved to extend the piston rod. Instead of returning to the reservoir, the fluid from the pump is sent to the lower chamber of the cylinder, forcing the piston up. The fluid in the upper chamber is forced out and travels through the control valve back to the reservoir. To retract the piston rod, the process is reversed. The valve spool is moved to the lower position, diverting fluid into the cylinder's upper chamber and forcing the piston down. The other principal component of a hydraulic system is the reservoir. The main purpose of the reservoir is to store excess hydraulic fluid. Other functions of the reservoir include cooling and cleaning the fluid and allowing air to escape from the system. Now, as you have probably guessed, there is more to a hydraulic system than the 4 components we have just talked about. For reasons of safety and reliability, hydraulic systems incorporate a number of protective mechanisms. We will look at these components in the next section. In the last section, you saw that a hydraulic system has 4 main elements: a pump, a cylinder, a control valve, and a reservoir. In addition to these components, there are a number of other devices whose purposes are to keep the fluid clean, protect the system from overpressure, and improve the safety of operation. We'll start with the fluid cleaning mechanisms. These include a vent filter, a strainer, a magnetic plug, and a return filter. For these components to work properly, they must be serviced at regularly scheduled intervals. We'll have more to say about this later when we talk about the pre-trip inspection. Earlier in the video, you saw that a hydraulic pump is kind of like the sorcerer's apprentice. Unless the operator shuts it off, it keeps on pumping, regardless of the system pressure. Think for a moment about what this means. What would happen if the operator forgot to return the control valve to the neutral position after the piston rod was fully extended or retracted? Unless the pump were turned off, the pressure would build up until something broke. To prevent this from taking place, a hydraulic system is equipped with a relief valve. When system pressure gets too high, the hydraulic fluid forces a small check ball in the relief valve to rise, allowing the fluid to bypass the control valve and return to the reservoir. Some other protective devices you should be aware of are the holding valves located on each of the hydraulic cylinders. In the event of system failure, the holding valves trap oil in the cylinders and prevent the affected systems from collapsing. You can think of a holding valve as a kind of one-way street, allowing fluid to flow in one direction only. Let's listen as our demonstrator describes the valve's operation.
Oil passes into the holding valve in this direction and directly over a check, as you can see in there, which it knocks off of its seat and enters the cylinder, this being a pad-mounted holding valve, directly into the cylinder, bolted in that direction. Cannot come up here because this check ball is on its seat. How do you get the cylinder back down? Oil would enter from this direction, from the up side of the cylinder. We'll knock this check off of its seat and go back to tank.
There is one final group of protective devices that are found on large insulated bucket trucks. On trucks with boom extensions over 40 feet, the hydraulic fluid has a tendency to drain from the boom back to the reservoir, causing a partial vacuum in the upper sections of the hydraulic hoses. If a vacuum forms in the insulated part of a hose, it reduces the boom's dielectric strength, resulting in an unsafe condition. To prevent this from happening, the upper boom is equipped with one or more anti-vacuum relief valves. If the pressure in a hose drops below atmospheric, its valve opens, allowing air into the line. The breather filter at the end of the valve must be changed at regularly scheduled intervals. In most utilities, as an operator, you will not be called upon to maintain the systems we have just been discussing, but you are responsible for making sure they are working properly. And that is what we will talk about in the next two sections. It's a fundamental rule that you never take a utility vehicle on the road without first performing a pre-trip inspection. As part of your circle check, you should examine the vehicle's hydraulic systems. You want to make sure they are clean and leak-free. When you carry out your inspection, the system should be warm, the engine should be running, and all cylinders should be retracted. It may seem surprising, but in the first part of your hydraulic check, you don't look at the vehicle. Instead, examine the vehicle's logbooks. Are the filters, strainers, or magnetic plug due for servicing? Does the oil need to be changed? If so, arrange to have the work done by a qualified mechanic. The next stage of your hydraulic inspection takes place at the reservoir. Start by checking the level of fluid in the reservoir using either the dipstick or the sight glass. Now, check the condition of the breather cap filter. If it's dirty, you will have to use an approved solvent to clean the washable screen. Do not use a rag to do this, or you may contaminate the system with lint. After cleaning the filter, be sure to dry it thoroughly, since any residual solvent could dilute the hydraulic fluid. In some cases, the breather cap filter has a paper cartridge. If it needs replacement, follow the manufacturer's instructions. Now it's time to check the condition of the hydraulic fluid. The importance of this step cannot be overstated. One manufacturer claims that as many as 70% of all service problems could be avoided by more frequent fluid changes. Some things to look for are a milky look, indicating the presence of water, a strong rancid odor, giving evidence of overheating, a black appearance, or the presence of grit or metal particles. After finishing at the reservoir, carry out the rest of your circle check. As you walk around the vehicle, look for fluid leaks, damaged hoses, loose fittings, and so on. This is a visual check only. Do not feel for leaks. Hydraulic fluid pressures can be as high as 3,000 psi. If you put your hand in front of a high-pressure fluid leak, you can be seriously injured. In the next section, we'll go over vehicle setup and holding valve checks. It goes without saying, you should never work from a vehicle unless you are sure it is stable. There are 4 basic steps involved in making a bucket truck or an RBD secure. Start by positioning the vehicle properly. Do not park right next to a curb or a hillside. Leave enough room to extend the outriggers all the way. Next, chock the wheels. Now, extend the outriggers to near maximum spread. On RBDs, take the full sprung weight of the vehicle without lifting the tires off the ground. On bucket trucks, make sure you can see the red indicator line. Put large flat pads under the outrigger feet to increase the contact area. And finally, level the vehicle to within 5 degrees side to side and front to back. Earlier in the program, we talked about the holding valves, which are an essential part of the safety systems of a bucket truck or RBD. Occupational health and safety regulations require that you inspect your vehicle's holding valves every day. To check the holding valves, you follow 3 basic steps, repeated with the components in different positions. Position the hydraulics. Turn off the engine or use the selector valve to disengage the hydraulics. Activate the controls. We'll run through this sequence in a moment, but first let's talk about the selector valve. Located near the mainframe controls, the selector valve is used to direct the hydraulic fluid either to the outriggers or the boom. If you use the selector valve as part of the holding valve checks, you have to be sure it's not leaking. Start by putting the outriggers down. Move the selector valve to the boom position. With the engine still running, try to retract the outriggers. You should not be able to see them move. Now you are ready to check the outrigger holding valves. With the outriggers still extended, turn the engine off or move the selector valve to disengage the outriggers. Activate the controls for 15 to 20 seconds. The outriggers should not retract. After checking the outriggers, restart the engine if necessary and put the hydraulic system through its paces. What you are doing now is purging the system, getting rid of any air, and freeing up the check balls in the holding valves. Now, check the holding valves on the boom cylinders, in the same way as you tested the outriggers. Position the hydraulics. Turn off the engine or disengage the boom. Activate the controls. On an aerial device, you check the holding valves with the boom in 3 different positions. Here is position 1. The upper boom is at least a foot off the rest. When you activate the controls, you should not see the cylinder move. Now test the holding valves with the boom in this position. And then repeat the tests with the boom as shown here. On a digger derrick, the test sequence is the same, but the boom position is different. After checking the outriggers and purging the system, raise the boom to approximately 60 degrees. Extend the stingers or extension boom halfway out, and carry out the holding valve checks as before. If the holding valves fail the tests, re-purge the system and try again. If there is still a problem, send the vehicle in for servicing. In this final section of the program, we will touch on some of the ins and outs of hydraulic equipment operation, starting with vehicle warm-up. The rule about warming up your hydraulic system is simple. Do it. Run the system through its paces before starting work. Give the hydraulic fluid a chance to circulate. If you are working in cold weather and have to shut the system down for more than an hour, go through the warm-up procedures again before starting work. One sign of a good operator is the smoothness with which they work the controls. Feather the controls when you are starting or stopping a movement. That way you will avoid shock loading the system. If you hear a sound like this, back the controls off right away. That's the relief valve operating, and it means you are overpressuring and overheating the system. And overheating is a major cause of fluid breakdown. If a particular job setup requires you to operate over center, or from a different bucket than normal, take extra care in working the controls. The control directions will be reversed. And still on the subject of controls, make sure that all ground personnel know how to work the lower controls in case of emergency, or in case the upper controls fail. We are almost at the end of this presentation on basic hydraulics. Before we sign off, let's take a moment to summarize some key points. Hydraulic power systems have 2 special qualities that make them particularly useful from a utilities point of view: mobility and dielectric strength. From a hydraulic standpoint, the most important part of a pre-trip inspection is checking the condition of the hydraulic fluid. Don't cut corners when setting up your unit. Make sure it is stable. Check the holding valves on your bucket truck or RBD daily. Work the controls smoothly. Listen to what the hydraulic system is telling you. The key word in dealing with your RBD or bucket truck is respect. Treat your unit properly, and it will return the favor.